Welcome to this explainer. Imagine, if you will, a massive steel structure weighing tens of thousands of tons. Now, drop that absolute behemoth into one of the most chaotic, unpredictable environments on Earth, the open ocean. How in the world does it stay upright? How does it survive a massive storm without just rolling over and sinking to the bottom? Well, the answer isn't just heavy metal or pure luck. It's actually a fascinating, incredibly high-stakes battle of mathematics. Today, we're going to explore the precise naval architecture that keeps these vessels afloat. We'll see exactly how officers use math to map out a ship's breaking point, and crucially, what happens when the chaotic forces of the sea decide to push back.
Here is our roadmap for today. 1. The science of ship stability. 2. Mapping stability with curves. 3. Calculating with cross curves. 4. The free surface threat. And finally 5. Surviving synchronous rolling. Let's jump right in.
Section 1. The science of ship stability.
Let's dive right into the foundational equation we're working with here, the moment of statical stability. It's calculated simply as W multiplied by GZ. Now W is just the displacement, literally the total weight of the ship in tons. And GZ? That's what we call the righting lever. Think of this moment of statical stability as the sheer physical muscle that fights to push a tilted ship back to an upright position. When a massive wave pushes a ship over, this mathematical product is the exact force pulling it back. And, as we're going to see, the size of that GZ righting lever is entirely dependent on the ship's center of gravity.
It's absolutely wild how this math translates directly into the physical, everyday reality for the crew on board. It all comes down to a ship's metacentric height, or GM. That's essentially the distance between its center of gravity and its tipping pivot point. Depending on that GM, a vessel behaves in one of two very distinct ways. A stiff ship has a high GM. It has a massive moment of statical stability. Now that sounds great, right? Well, it means it takes a lot of force to incline it, but when it does roll, it snaps back violently and quickly. It's a really short time period and incredibly uncomfortable for the crew. On the flip side, a tender ship has a small GM. It inclines super easily and has a long, slow time period to return to upright. It's a much smoother ride for sure, but the trade-off? You have far less statical stability, keeping you safe from capsizing.
Section 2. Mapping stability with curves.
To predict how a ship will behave at various angles of heel, naval architects create a statical stability curve. And guys, this isn't just some simple graph. It is a vital predictive map. By plotting the righting levers against the angle of heel, officers can instantly identify a massive amount of data. They can see the total range of stability, the absolute maximum righting lever they can rely on, the initial GM, the point of inflection, and, perhaps most terrifyingly, the angle of vanishing stability. That's the exact degree of tilt where the ship's ability to right itself drops to absolute zero.
Now, when looking at these curves to find the initial GM, officers use a very specific, seemingly random number, 57.3. You might be wondering why that number. Well, they draw a tangent to the curve through the origin and erect a perpendicular line at exactly 57.3 degrees of heel. Where they intersect gives the initial GM. The reason for the specific angle is pure geometry. 57.3 degrees is exactly equal to 180 divided by pi. In other words, 57.3 degrees is exactly 1 radian.
Let's consider another absolutely crucial point on that curve, the point of inflection. Mathematically speaking, it's just the angle where the curve changes from being concave to convex. But the physical significance of this point, the stakes couldn't be higher. This abstract data point marks the exact angle of heel where the edge of the ship's deck physically touches the surface of the sea. It is the literal tipping point where the geometry of the ship's interaction with the water fundamentally changes. Of course, stability isn't just about rolling around in the waves. It's also about loading the vessel properly. And this brings us to the hydrostatic curve. Think of this as a complementary tool that maps the ship's draft against values like tons per centimeter, displacement, and centers of buoyancy. If you were to just average the forward and aft drafts of a huge vessel, you could actually create appreciable, dangerous errors in calculating your displacement. So the hydrostatic curve allows officers to interpolate the true mean draft, ensuring that when cargo is added, discharged, or shifted around, the resulting stability calculations are dead accurate.
Section 3. Calculating with cross curves. There is a remarkably clever shortcut to the practical problem officers face out at sea. A standard GZ cross curve is plotted for an assumed center of gravity, known as kg. But out on the water, your actual kg is almost never the assumed kg, which means you're constantly stuck calculating a correction. To make things simpler, naval architects often use KN curves instead. A KN curve is the exact same concept, but it assumes the center of gravity is exactly 0 meters, literally right at the very bottom of the keel. Because your actual center of gravity will always be higher than 0, you just find your actual righting lever by subtracting a correction from the KN value. It streamlines the whole process.
Let's see how this actually builds into real-world application. Imagine a ship displacing 40,000 tons with an actual center of gravity, our kg, 10 meters above the keel. Let's consider a 30-degree heel. The naval architect's KN curve gives us a value of 6.30. To find the real righting lever, we calculate our correction. Our 10-meter kg multiplied by the sine of the 30-degree heel. Well, 10 times 0.5 gives us exactly 5.0. We just subtract that 5.0 correction from the 6.30 KN value, leaving us with a true corrected GZ of 1.30 meters. And there you have it. This is exactly how the crew constantly adjusts the theoretical math to match the physical reality of their cargo.
So the absolutely crucial takeaway here is this universal correction rule for cross curves. If you're using a standard curve and your actual center of gravity is higher than the assumed one, you must subtract your correction. Basically, the higher your center of gravity, the less stable the ship becomes. If your actual center of gravity is lower than assumed, you add the correction, which gives you a wider margin of safety. It's a zero-sum game of weight distribution, and getting it right is non-negotiable.
Section 4. The free surface threat.
Now, daily operations on a ship involve consuming fuel, drinking water, and moving ballast around. This means the tanks below deck are rarely perfectly full or totally empty. Think of trying to walk while carrying a half-filled baking pan of water versus a solid block of ice. If a tank is fully filled, the liquid simply cannot move. It acts as a static, solid weight, and its center of gravity remains completely constant even when the ship rolls. But in a partially filled tank, the liquid is completely free to flow. As the ship heels to one side, thousands of gallons of water or oil rush in the direction of the heel. The center of gravity of that fluid violently shifts.
The terrifying consequence of this shifting fluid is what naval architects call the free surface effect. As the fluid's center of gravity shifts outward, it causes the overall center of gravity of the entire ship to virtually shift outward as well. If you trace that geometry back up to the center line, it creates a new, higher, virtual center of gravity. This results in a virtual loss of metacentric height. The sloshing liquid literally subtracts from the ship's calculated ability to right itself. You could be up on the bridge thinking your ship is perfectly mathematically stable, but the hidden movement of fluids below deck might be severely compromising your safety.
Section 5. Surviving synchronous rolling.
Every single ship has a natural rolling period, the time it takes to roll from one side to the other and back again. But waves also have a period. Synchronous rolling occurs when the ship's natural rolling period becomes completely resonant with the passing wave period. When these two rhythms sync up, the ocean effectively pushes the ship exactly when it is already rolling, amplifying the heel with every single wave. It's exactly like pushing a kid on a swing at just the right moment to make them go higher and higher. But we're talking about tens of thousands of tons of steel here. In exceptional circumstances, this resonance forces the vessel to heel beyond its vanishing point, resulting in negative stability and an inevitable capsize. Without a doubt, it is one of the most dangerous phenomena at sea.
When a ship enters synchronous rolling, the crew doesn't have time to form a committee. They must act immediately to break that deadly rhythm. They essentially have three primary options. First, pump water ballast. This instantly alters the ship's center of gravity, changes the metacentric height, and forces a new, non-synchronous rolling period. Second, change the course heading. Doing this alters the frequency of the waves hitting the hull. And third, alter the ship's speed. Speeding up or slowing down changes the wave encounters and instantly breaks the resonance.
We can plot hydrostatic curves to perfectly interpolate our draft. We can calculate our GZ righting levers using KN tables down to the exact decimal point. We can even account for the virtual loss of stability from the free surface effect. But out on the open ocean, when a massive storm triggers synchronous rolling, the math is really just a baseline. At that critical moment, is the math enough to save the ship? Or does survival ultimately depend entirely on the crew's ability to react, shift ballast, and steer their way out of the ocean's deadly rhythm? It's definitely something to think about the next time you look out at a freighter on the horizon. Thanks for joining me for this explainer, and keep learning.